Research on Legged Machines. Before introducing the main topic of this book, the study of machines that run using active balance, we turn briefly to an account of the previous work on legged machines. The scientific study of legged motion began over a century ago when Leland Stanford, the governor of California, commissioned Edward Muybridge to find out whether or not horse left the ground with all 4 feet at the same time. That's a trotting horse. Stanford had wagered that it never did. After Muybridge proved him wrong with a set of stop-motion photographs that would appear in Scientific America in 1878, Muybridge went on to document the walking and running behavior of over 40 mammals, including humans. His photographic data are still considered valuable and survive as a landmark in locomotion research. The study of walking machines also had its origin in Muybridge's time. An early walking model appeared in about 1870. It used kinematic linkage to move the body along a straight horizontal path, while the feet moved up and down to exchange support during stepping. The linkage was originally designed by the famous Russian mathematician Shebaev some years earlier. During the 80 or 90 years that followed, workers viewed the task of building walking machines as the task of designing kinematic linkages that would generate suitable stepping motions when driven by a source of power. Many designs were proposed, but the performance of such machines was limited by their fixed pattern of motion, which could not adjust to variation in the terrain. By the late 1950s, it had become clear that a linkage to provide fixed motion would not do the trick, and that useful walking machines would need control. One approach to control was to harness a human. Ralph Mosher used this approach in building a 4-legged walking truck at General Electric in the 1960s. The project was part of a decade-long campaign to build better teleoperators capable of providing better dexterity through high-fidelity force feedback. The machine Mosher built stood 11 feet tall, weighed 3,000 pounds, and was powered hydraulically. It is shown in Figure 1.5. Each of the driver's limbs was connected to a handle or pedal that controlled one of the truck's 4 feet. Whenever the driver caused a truck leg to push on an obstacle, force feedback let the driver feel the obstacle as though it was his or her own arm or leg doing the pushing. After about 20 hours of training, Mosher was able to handle the machine with surprising agility. Films of the machine operating under his control show it ambling along at about 5 miles per hour, climbing a stack of railroad ties, pushing a founder jeep out of the mud, and maneuvering a large drum onto some hooks. Despite its dependence on well-trained human for control, this walking machine was a landmark in legged technology and continues to be a significant advance over many of its successors. An alternative to human control of legged machines became feasible in the 1970s. The use of a digital computer. Robert McGee's group at Ohio State University was the first to use this approach successfully in 1977. They built an insect-like hexapod that could walk with a number of standard gaits, turn, grab, and negotiate simple obstacles. The computer's primary task was to solve kinematic equations in order to coordinate the 18 electric motors driving the legs. This coordination ensured that the machine's center of mass stayed over the polygon of support provided by the feet, while allowing the legs to cycle through a gate. The machine traveled quite slowly, covering several meters per minute. Force and visual sensing provided a measure of terrain accommodation in later developments. The hexapod provided McGee with an excellent opportunity to pursue his earlier theoretical findings on the combinatorics and selection of gait. The group at Ohio State is currently building a much larger hexagon, about 3 tons, that is intended to operate on rough terrain with a high degree of autonomy. Garfunkel and his co-workers in the USSR built a machine with characteristics and performance quite similar to McGee's at about the same time. It used a hybrid computer for control, with heavy use of analog computation for low-level functions. Heroes realized that linkage design and computer control were not mutually exclusive. his experience designing clever and unusual mechanisms, he had built 7 kinds of mechanical snake, led to a special leg that had simplified the control of locomotion and could provide efficiency. The leg was a 3-dimensional pantograph that translated the motion of each actuator in a pure Cartesian translation of the foot. With the ability to generate X, Y, and Z translations of each foot by merely choosing an actuator, the control computer was freed from the arduous task of performing kinematic solutions. Actually, the mechanism linkage was helping to perform the calculations needed for locomotion. The linkage was efficient because the actuators performing only positive work in moving the body forward. Heroes used this leg design to build a small quadruped about 1 meter long. It was equipped with a touch sensor on each foot and an oil-damped pendulum attached to the body. Simple algorithms used the sensors to control actions of the feet. For instance, if a touch sensor indicated contact while the foot was moving forward, the leg would move backwards a little bit, move upward a little bit, then resume its forward motion. If the foot had not cleared the obstacle, the cycle would repeat. The use of several simple algorithms like this one permitted Hirosei's machine to climb up and down stairs and to negotiate other obstacles without human intervention. These 3 walking machines, McGee's, Gerfinkel's, and Hirosei's, represent a class called static crawlers. Each differs in the details of construction and in computing technology used for control, but they share a common approach to balance and stability. Enough feet are kept on the ground to guarantee a base of support at all times, and the body and legs move to keep the center of mass over this broad support base. The forward velocity is low enough to predict stability based on the spatial configuration of the body and feet, without worrying about stored energy. Each of these machines has been used to study rough terrain locomotion in the laboratory, including experiments on terrain sensing, gait selection, and selection of foothold sequences. Several other machines that fall into this class have been studied in the intervening years. Research on active balance. This last section focuses on legged machines that use static techniques for balance. We now turn to the study of dynamic machines that balance actively. The first machines that balanced actively were automatically controlled inverted pendulums. Everyone knows that a human can balance a broom on their finger with relative ease. Why not use automatic control to build a broom that can balance itself? Claude Shannon was probably the first to do so. In 1951, he used the parts from an erector set to build a machine that balanced an inverted pendulum atop a small powered truck. The truck drove back and forth in response to the tipping movements of the pendulum, as sensed by a pair of switches at its base. In order to move from one place to another, the truck first had to drive away from the goal to unbalance the pendulum toward the goal. In order to balance again at the destination, the truck moved past the destination until the pendulum was again upright with no forward velocity. It then moved back to the goal. It was Shannon's urging that the Cannon and 2 of his students at Stanford University set about demonstrating controllers that balanced 2 pendulums at once. In one case, the pendulums were mounted side by side on the cart, and in another case, they were mounted one on top of each other. Cannon's group was interested in the single input, multiple output problem and the limitations of achievable balance. How could they use the single force that drove the cart's motion to control the angle of 2 pendulums, as well as the position of the cart? How far from balance could the system deviate before it was impossible to return to equilibrium? Given the parameters of a mechanical system, e.g. a cart, strength, and pendulum lengths. Using analysis based on normal coordinates and bang-bang switching curves, they express regions of controllability as explicit functions of the physical parameters of the system. Once these regions were found, their boundaries were used to find switching functions that provided control. Later, they extended these techniques to provide balance for a flexible, inverted pendulum. These studies of balance for inverted pendulums were important precursors to later work on locomotion. The inverted pendulum model for walking would become the primary tool for studying balance in legged systems. It is unfortunate that no one has yet extended Cannon's elegant analytical results to the more complicated legged case. Mosher's group at General Electric was also interested in balance. Their original intention, before deciding to build the quadruped described earlier, was to build a walking biped that would be controlled by a human who would walk in an instrumented harness inside the cockpit. They started with a human factors experiment because they were unsure of the human's ability to adjust to the exaggerated vestibular input that would be experienced when one drives a machine several times taller than oneself. In the experiments, the subjects stood on an inverted pendulum about 20 feet tall. The pendulum had pivots like an ankle and a hip, one at the floor and one below the platform that supported the subject. These pivots were servoed to allow the corresponding ankle and hip motions of the subject. All 86 people tested learned to balance the machine in less than 15 minutes, and most learned in just 2 or 3. Although the GE walking truck mentioned earlier could, in principle, operate using purely static techniques, the driver's ability to balance it actively probably contributed to its smooth operation. A GE walking biped was never built. The importance of active balance in legged locomotion has been widely recognized for some years. But progress in building physical legged systems that employ such principles was retarded by the perceived difficulty of the task. It was not until the late 1970s that experimental work on balance in legged systems got underway. Kato and his co-workers built a biped that walked with a quasi-dynamic gait. The machine had 10 hydraulically powered degrees of freedom and 2 large feet. Generally, this machine was a static crawler, moving along a pre-planned trajectory to keep the center of mass over the base of support provided by the supporting foot. Once during each step, however, the machine temporarily destabilized itself to tip forward, so that support would be transferred quickly from one foot to the other. Before the transfer took place on each step, the catching foot was positioned so that it would return the machine to equilibrium passively, without requiring an active response. A modified inverted pendulum model was used to plan the tipping motion. In 1984, the machine walked with a quasi-dynamic gait, taking about a dozen half-meter-long steps per minute. The use of a dynamic transfer phase makes an important point. A legged system can employ complicated dynamic behavior without requiring a very complicated control system. Miura and Shimoyama built the first walking machine that really balanced actively. Their stilt biped was patterned after a human walking on stilts. Each foot provided only a point of support, and the machine had 3 actuators, one for each leg that moved the legs sideways, and a third separated the legs fore and aft. Because the legs did not change length, the hips were used to pick up the feet. This gave the machine a pronounced shuffling gait, like a Charlie Chaplin stiff-kneed walk. Once again, control for the stilt biped relied on an inverted pendulum model of its behavior. Each time a foot was placed on the floor, its position was chosen according to the tipping behavior that was expected from an inverted pendulum. Actually, the problem was broken down as though there were 2 pendulums, one in the pitching plane and one in the rolling plane. The choice of foot position along each axis took the current and desired state of the system into account. In order to perform the necessary calculations, the control systems used tabulated descriptions of planned legged motions together with linear feedback. Unlike Kato's machine, which came to static equilibrium before and after each dynamic transfer, the stilt biped tipped all the time. Matsuoka was the first to build a machine that ran, where running is defined by periods of ballistic flight with all feet leaving the ground. His goal was to model repetitive hopping in the human. He formulated a model consisting of a body and one massless leg that he simplified the problem by assuming that the duration of the support phase was short compared with the ballistic flight phase. This extreme form of running, for which nearly the entire cycle was spent in flight, minimized the influence of tipping during support. This model permitted Matsuoka to derive a time-optimal state feedback controller that provided stability for hopping in place and for low-speed translations. To test his method for control, Matsuoka built a planar one-legged hopping machine. The machine operated at low gravity by lying on a table inclined 10 degrees from the horizontal, rolling on ball bearings. An electric solenoid provided a rapid thrust at the foot, so the support period was short. The machine hopped in place at about 1 hop per second and traveled back and forth on the table.